Yes, thank you for the introduction and also for the invitation to Prague. I've never been here, so I'm enjoying my visit very much. So the title of my talk is Automatic Generation of MultiNet Representations for German Text Corpora. So I'm not really talking about text generation. So it's might be confusing title. Okay. What I will present is mostly joint work with Ingo Glöckner, Hermann Helbig, Johannes Leveling, and Rainer Oswald. We are all at the Fernuniversität in Hagen. And let's see. Here's a short overview of my talk. I will give a brief motivation for our approach to natural language processing. For this, I need a short description of the target representation, the semantic target representation we are working with. And the third part, I will talk a little bit about our parser. And we'll go on to disambiguation problems and how we solve it in our context. Then I will present some facts about our coreference resolution, and finally semantic assimilation, which is a whole bunch of post-processing steps after the parser has ended. I will show you some applications which all build on deep semantic analysis, and after the conclusion I will show you some of our future work plans. So for motivation, our view is something like this. There's many success stories for NLP applications which rely only on shallow methods. And but we think that there are many more NLP applications which call for deep methods. And so what I'm talking here about is deep semantic analysis of large text corpora. So as you all know, we have many steps and methods which span this range from real-world text corpora to formal semantic representations, and then it's an additional problem, the successful exploitation in applications. So as I said, I must present the target representation which we are working with, and this is the semantic network formalism MultiNet, which was presented here in this room, I guess, 1 year ago by Professor Helbig. So I will just give a brief overview. It provides means for homogeneously representing the semantics of words, or also multi-word expressions, phrases, sentences, text, and whole text corpora. Here, as a starter, we have a small MultiNet, a semantic network of the MultiNet formalism. Die Mutter gab ihrem Sohn ein neues T-Shirt is the German sentence. The mother gave her son a new T-shirt. And just to give you an impression of the semantic network, as you can see, the central concept corresponds to the verb, and it also appears in the center of the semantic network. I should add that this graphical form might look unfamiliar to you because here are some edges which are folded below the node. So actually all the sub edges are folded below the node, which means I could also draw an edge labeled sub for subsumption to zone, son. So this is just a simplification which makes it easier to lay out semantic networks. So I will show you the details of the semantic representations later on when I talk about this in the context of parsing. So syntactic semantic parser we are working with is called Vocadi, and it forms the center of the whole MultiNet approach. It has a classical structure, so I want to say some words about the morpholexical analysis, which comes first. We have 3 completely different lexica. The first one is we often call it a deep lexicon. Its name is Hagenlex, stands for Hagen German Lexicon. And it provides full information on orthography, morphology, syntax, semantics, especially from a valency point of view. We have currently 26,000 entries, 13,000 for nouns, 8,000 for verbs, and 3,000 for adjectives. Of course, this is too small to parse real-world text, so we have, in addition, a flat lexicon. Flat in the sense we have no semantics, no valency frames in this lexicon. And this gives us around 50,000 additional entries. This is also always base forms, not full forms. As you know, German has a rich inflection, so word form numbers are by a factor of 5 or 6 higher than these numbers that I have on the slide. And we have extracted these entries from CLEX and UMLS. And finally, we have a lot of name lexica, around 100 lists, which give us around 500,000 entries. And these are for very different concept classes like city, country, region, product, things like this. So some of them are manual maintained, especially the important ones like the country list, but some others are, the longer ones and not so central ones, are extracted from Wikipedia. Okay. To give you an example of our deep lexicon, this is an entry from Hagenlex for the verb that we saw before in the figure number 1. So it will just jump back. You remember this semantic network. And as you can see, all arguments, we have 3 arguments of the verb connected by an agent, orientation, and an object relation. And the corresponding Hagenlex entry, which allows us to analyze the sentence in the way I've shown you, also contains the 3 arguments, and you see the complement relations appear again here. And you also get a small impression that we have on the morphological side. We have the base form, the inflectional paradigm. On the syntactic side, we have information about the perfect auxiliary, which we need in German, the semantic class, the concept ID, in this case, game 1.1.2. So then the valency under the select feature, and each argument is characterized by syntactic realization. For example, the agent is here as usually a noun phrase and nominative. And you also see examples of selectional restrictions on the semantic side, where we have semantic features like potential agent or legal person. Okay, and because it comes back later, I will also explain you the last feature. We have one or several example sentences for each entry in our lexicon. And as you can see, it contains some structure. So we have marked up the complements by simple parentheses. And we can use this as a test corpus for our parser, as I will show you later. So for the morphology part of morpholexical analysis, we have derived our morphology from CLEX. In addition, we need a sophisticated compound analysis. Our analysis is semantically oriented because we also need the semantics for the MultiNet. As you might know, compounds are very productive in German, and if you don't know anything about compounds, you won't understand many texts. So it's very popular, and so we have decided for better disambiguation, we need a special compound lexicon, which currently contains 30,000 entries. And it's a very lean format. We just specify the segmentation and the semantic class. So here's an example for a partially ambiguous one. Staubecke and Staubecken. You can see the segmentation is different. And also the semantics, which is just a semantic name, is different. And we maintain this semi-automatically. That means we have most entries in this lexicon come from automatic analyses. And if some person invests time to check them, then we add this author date part so that we know this was manually checked. So to explain the meaning, if we have a word form of this compound, Staubecken, this could mean dust corners or reservoir or water reservoir. So it's really important to get the segmentation right. So not about the parser itself. This builds on word class function analysis, which is some years old. So I will explain you why we use it. So first, there might be a problem, and there is a problem because we have no clean separation of parser and grammar. So as you can see by publication, it was started in the 80s where this was really no problem. So from current point of view, it's somewhat problematic for maintenance. So why do we use it? Because first, we have long experience, and so it's a really experienced workhorse, this parser. And on the other hand, it's turned out to be really easily extendable. For example, we have in our research we are not focusing on parsing at its center, but we focus on things like disambiguation. And this parser allowed us to plug in different disambiguation modules. So we have re-implemented the whole parser in the scheme programming language, and as I said, it's called Vocadi, which stands for word class based disambiguating parser. This is an overview of the architecture, the parser. I will just explain some of the modules to give you an overview. So the data flow is shown here, and starts with the user or application which provides natural language text. Then we have a pretty standard order of modules like a word sentence tokenizer, morpholexical analysis, with 3 different lexica, which I explained to you shortly. And what comes out from this step is a list of feature structures for all the words in the text. Then the central WCF machine with all these word class functions, which will explain you later, come into play. What is important here is that we have different disambiguation models, like I've shown two of them, like for prepositional phrase disambiguation and for coreference resolution. And here both models have 2 main sources. First are manual written interpretation rules, and the second one are disambiguation statistics, which we gained from annotated corpora. And what comes out from the parser is a semantic representation of the MultiNet formalism, which are further refined by several models which I labeled refinement components, so that we end up with a second semantic representation also in the MultiNet formalism, which can go back to the user or to intermediate system. I just want to mention some of the characteristics of the word class function analysis. So we have for each word class, which is similar to some set of part of speech, we have a word class function implemented. And these word class functions, together with the central control mechanism, the WCF machine, model 2 phases of word activity. So this has some similarity to chart parsing, that we have 2 different acts for each word class. The first one is the opening act, and the second is the completing act. So as the name indicates, the first one opens expectations about what might follow after the current word, which we are investigating. And the completing act collects all the surrounding constituents, like complements, adjuncts to the heads, so that the expectations get saturated. What is important for my talk is that we are oriented towards constructing multinets. So syntax is just a useful byproduct from our point of view. We concentrate on semantics, and another characteristic is that we emphasize on understanding natural language sentences which are acceptable to normal hearers or readers, but not on perfectly grammatical sentences. So the whole parser works on different levels. I've shown you 4 of them. The first is deals with elementary kernels, we call them, which are, for example, simple MPs. On the second level, we talk about complex MPs. Then on the third level, we operate with simple proposition. So all phrases which contain just one verb. For example, this would be a clause. And on the highest level, we deal with complex propositions, complex sentences. So just because people asked, I have on the slide a small example of such a word class function. This is for the adverb. I prepare 2 bindings where I have the syntactic category of the next word, which means that we have a look ahead of one word in the parser, and we have I assign the semantic sort of the current word to this variable. So And then we have a construct, follow alternatives, which allows us to open from the point of view of the current word all the alternatives it could imagine. So this is the first alternative, pseudocode. We have the condition, if the next word is an adverb, and the current, and we already know that we are working on an adverb because this is the VCF of an adverb. Then we assume that the adverb modifies another adverb, and we can record the expectation that we expect an adverb phrase. So, and similarly, we have the case that we actually are expecting an adjective phrase because the next word looks like an adjective. Okay, I was asked to talk about MultiNet construction, especially because in Prague some people started a project to build multinets by hand. Work initiated by Václav Novak. And so I will show, maybe in contrast, maybe in addition, how the Parser does the multinet construction. As an example, to show you some of the elements of multinet in action is a clay corpus sentence, which just read the English translation. After the communists gave up their power monopoly, Karadzic moved to politics and founded in 1990 the Serbian Democratic Party, SDS. So the multinet, which the parser generates, looks like this, and I just want to show you the three aspects which we'll explain in the following of a multinet. First of all, we have all the edges which bear relation label, like the semantic row labels agent, which we have seen before, or affected object. This is just one layer of multinet, and I will explain how we can achieve this layer. Then you also see that each node has some inner structure. For example, if you look at this node C9001, that's a generated name for an instance. But what is important, you also have this cryptic inner structure, which I will explain, which corresponds to the layer features of the multinet formalism. So this is the second element of multinets which the parser has to deal with. And the third element is that also the relations themselves have some inner structure, meaning some attributes. As you can see, each arc has some marker at the start, the C, and here an S at the end. And these are the so-called knowledge types, which is the third level of multinets, which also must be, as you see in this example, must be generated in some form by the machine. Okay, now I will explain the three layers in detail, how we generate them. So, the relational layer is just, as I said, the labels on the edges. And where do all these multinet parts come from? So there are many sources. The first one are, of course, the WCFs themselves. For example, if we have an adjective, the corresponding word class function can generate the semantic contribution of the adjective, which is can be, depending upon the sort of the adjective, can be a property edge or relational property edge or a functional modification. So for example, the word class function for adjectives has generated these prop edges that you see on the left side, which are the attributes of the party, like democratic and Serbian. So the other sources are all from the lexicon. So for the relational layer, the lexicon is probably the most important part. As I have shown you in the example entry for the verb given, the valency frame of verbs, nouns, adjectives contains relations for their arguments. And typically, each argument gets just one relation, but in general, it can also be several relations, which means that we have a set-valued feature for each element of the valency frame. We have a rel feature, which just contains a set of features, the set of relations, which go from the verb or the head in general to the argument. So the example network from the beginning on the lexical entry, these were there were three arguments, and they got the three relations I've repeated here: the agent, orient, and the object. So there are some cases where this approach to specify semantic rows doesn't suffice, and for these cases we have a special feature, net, which also can appear on verbs, nouns, and adjectives, and some other word classes. And this is needed if we want to specify a whole semantic network which connects the argument to the rest of the situation, for example. Here's an example from German, bestehen, in this reading, which means something like the reading, the table consists of wood. And so in this case, semantically, it is not too interesting to look at the semantic relations from the arguments to the verb bestehen, but what is the real center of the meaning is the relation between the arguments. In this case, it means that the first argument has some material origin, as we call it, to wood. And so in this case, we have no interesting relation leading from the verb to the argument, but we have a special net, which contains oric m, which means material origin from x1 to x2. x1 is the first argument, x2 is the second argument. So we call this a meta verb from a MultiNet point of view because it is actually this verb is just an expression for a MultiNet primitive. I should have mentioned that the set of relations which we can use in MultiNet is predefined, around 100 plus some functions. So they have a special status, all these functions, all these relations which I have talked about, like agent orientation. This is a closed class, and some of them can be described by just a natural language verb, for example. But there are other cases where we use this network, for example, for prepositional verbs. It's often necessary to express the semantics of the verb on this network level because semantic relations make no good distinction between readings and similar verb readings. And the semantic network feature is also important for prepositions and similarly for conjunctions. So we can have, typically a preposition can have many readings, and each reading has a completely different semantic network. So for this, with this mechanism, we can analyze the difference between these two English phrases, both containing in prepositional phrase, like the shot in the morning versus the shot in the darkness. The first one has some temporal interpretation, while the second is more like a circumstance, for example. One can see these, by the way, one can see these different entries for preposition also as special interpretation rules for prepositional phrases. And we have done this in a paper at ESAL last year. So there are some more features in our lexicon which contain MultiNet parts. I will just describe the idea of some of them. AntNet is intended to contain entailments in the form of semantic networks, and this is of course especially relevant for verbs. And we currently store entailments in a semi-formal way, because it's much easier for the lexicographer to specify them in a format which is close to natural language, and we automatically translate them to full semantic representations. An example would be that we have stored at verbs that mean something like to murder. We have the semi-formal entailment would look like x2, the second argument dies, as an entailment. So, and we can translate these regimented natural language form to full semantic network, which will be stored in this AntNet feature. Similarly, we have also sometimes cases where we can specify equivalence, which is, in our view, a special case of entailment in both directions. We also use some semantic relations for relating lexical concepts. This is especially interesting for synonymy, antonymy, etc. We are also using a mapping to German WordNet, which is called GammaNet, to enrich our resources to fill some of the synonymy, antonymy relations we will need in processing. On the list I also have mentioned presuppositions and selection restrictions, but they are only in the planning, so it's not realized currently. For selection restrictions, normally we specify just semantic features for the argument. For example, this must be a human object, or this must be an animal. But in some cases, this semantic feature system is not fine enough. For example, if you have a meaning of something like the clock ticks, you have a German reading that corresponds to a tick, which just allows something like a bomb or a clock, nothing else. So you really have to specify a very specific selection restriction, and this CellNet feature allows us to do this. So this was all about the relational layer of MultiNet. Now I come to the second part of the three layers I want to show you. This is the inner structure of MultiNet nodes. You maybe remember these from the talk by Professor Helbig, but I will show you just the quick overview of this. The important point is that we have in In total, we have seven different layer features, but they don't belong to all nodes, but only to very specific ones. For example, as the names indicate, this is a type hierarchy, I should say. The type hierarchy, which starts on the left and goes to the right, we have this C lay, and the C stands for situation, which corresponds roughly to verbs. And as you can read from the type hierarchy, for verbs we just have two layer features, namely fact for facticity and gener for genericity, which I'll explain in a minute. And then we have this specialization to O-lay. This corresponds roughly to all the objects, which have, in addition, 5 layer features. And all the other nodes have no layer features at all. Here's a short overview of the features. You can think of them, 4 of them as intentional on the intentional level and 3 of them on the extensional level. So genericity is the contrast between generic versus specific uses. The quant feature contains quantification information. Refer is the difference between determinate and indeterminate. And varia is the variable reference. On the extensional side, we have these 3, like cardinality, which corresponds to quant on the intentional layer. For example, if you have something like 11 players did this and this, then the number 11 will end up in this cardinality feature. Extension type is for contrasting individual sets of individuals, set of sets, etc. And finally, we have facticity, which has 3 different values: real, hypothetical, and non-real. So now the task is that the parser must add all these layer features to corresponding nodes. And again, the main source is the lexicon. For example, if you think about determinants and quantifiers, they all can have, if you want to say so, they have lexicalized layer features, values. Like, of course, if you have a number, you already know the cardinality. It will contribute to noun phrases, for example. And also, on the semantic side, if you have a distinction marker between count nouns and group nouns, then you can also know the extension type. The extension type would be 0 for count nouns, and group nouns would be 1 in general. So the second source is the word class functions. For example, if the word class function for nouns is responsible for modifying E-type. So a singular E-type, for a singular count noun, E-type would be 0, which corresponds to this individual case. And in the plural case, this E-type goes up by 1 to 1. So basically, this word class function must look at the syntactic number feature. And the PP interpretation rules can influence layer features of nodes. Prominent examples are cardinality and E-type. This is basically for all the prepositions which behave similarly to conjunctions on the semantic level. If you think about mid, with in English, this semantically it behaves like a conjunction, and therefore you have information. You have to propagate information about cardinalities and so on. If you think about sentences like four people with 3 cars or things like this. And finally, we have a layer unification principle, which is enforced in all the word class functions which participate in nominal phrases. For explanation, for example, if you have the phrase these 5 students, then all 3 words have local information about some layer features. For example, these will have from the lexicon information that this is a determinate reference. 5 would, as I said earlier, would specify the cardinality of 5. And finally, the student itself is a normal count noun, so that the E-type is restricted. And if you take all this information by unification together, you get a complete layer structure with 7 layer features as required by the MultiNet formalism. But I must add that some post-processing is needed. For example, currently the parser doesn't try to distinguish generic uses from specific uses. So for this we have a MultiNet workbench, and it contains a specific module for all the layer features. And this is a way to go after parsing to get a full MultiNet representation. But for most applications, for example, the layer features as delivered by the parser, which I described on this slide, is sufficient. But in some cases, if for example, you want to try to learn generic knowledge about the world, then you have to detect distinguish generic uses from specific uses, for example. So then you would go to this MultiNet workbench. So this is the third and last layer which we have in MultiNet. These are the layer features of relations. I should go back to example. The relations, as I said earlier, have 2 so-called knowledge types indicated by a letter in this graphical form. The C stands for categorical and S stands for situational. For example, here you have the situation node for to give up, and all the arguments are categorical for the situation, because without the arguments, that situation doesn't exist. So, but on the other side, if you view the agent relation from the communist node on this side, this is just situational knowledge about communists. They are not defined by the fact that they act in this or occur in this situation on the right side. They just happen to be mentioned in this context, but the situation itself is defined, and therefore this knowledge is categorical on this side. So how do we get this information in the parser? I've mentioned categorical and situational. These are just 2 values. We also distinguish on the immanent, on the definitional part, the case that we have prototypical information. So the sources for all this is first that we have some defaults, and the default is specified per relation. So each relation has default knowledge type from the point of view of the starting node and the end node. So then, again, some VCFs can refine this information. Currently, this is mainly about refinements from situational to categorical. It's not a logical refinement, but so, for example, if you have a genitive NP, we can often assume that the modified NP is categorically described by the genitive, for example. And again, in PP interpretation, we have some cases where we can specify explicitly k-types. But similar to the layer features of nodes, there are some cases where we need post-processing, and again, this is handled by the MultiNet Workbench layer module. Okay, this was a MultiNet part. I would like to tell you some values from evaluation of the parser. I have 4 corpora listed, quite diverse range. The first 2 are very small. You probably know Tübats, Tübingen Tree Bank of Written German, which contains around 27,000 sentences. Then I have listed a strange corpus. It's called Hagenlex Examples. When I was writing the slides, I came up with the idea that you could view this as a corpus, but it's very specific. As I said, we have example sentences for each entry. So in total, we have currently around 24,000 examples. And they have the nice feature that they are, I will explain you later, that they are covered by the lexicon more completely. So performance statistics are interesting to compare for general corpora and for our example sentences. Then we have 2 real corpora from size point of when looking at the quantity. For example, we have a clay corpus, which contains around 5 million sentences with 90 million words. And recently we tried some Wikipedia snapshots. This one here is 6 months old and already contains 11 million sentences and 200 million words. So we have measured coverage on these, around 60% for correct sentences. Interesting cases, of course, Hagenlex coverage is near 100%. That's not too surprising because, as I will tell you later, the main problem, or one main problem, is the lack of deep resources, meaning lack of lexical entries. And in these Hagenlex examples, this area is ideally covered because at least if we have a Hagenlex example sentence for a given verb, we know that this verb is in Hagenlex, and of course the parser uses Hagenlex for parsing. So from a lexical point of view, it's an ideal corpus. And it's, in addition, it's an easier corpus because all the examples must follow some regimented form, as you might have seen in the lexicon example. So why not higher? 60%, yes, that's really embarrassing. And if I come to Prague or other places, and it's only 60%, yes. I must say we are working on mainly on applications of NLP techniques, and as I said earlier, parsing is not our research area. We use the parser for experimenting with disambiguation, but in the recent past we work mainly with semantically oriented applications like question answering, and there we have, for example, some redundancy in the data. So it's often the case in question answering that the fact you are looking for, the answer you are looking for, occurs in many sentences. So we are not so embarrassed that we lose like 40% of the sentences. And but let me, this was a pragmatic view. Let me explain a little more why this is so low from your point of view, I guess. Of course, we are not only doing syntax, but also semantics. And I have a rough figure here. Of course, the coverage rates multiply. So if we, from a syntactic point of view, if we have something like 0.8 coverage, and a semantic point of view, we have a similar coverage. Okay, we end up with a total coverage of 64%, which is quite like the 60% which are measured on Clay and Wikipedia. So what would be needed if we want to go to come closer to the coverage of syntactic parsers? I've listed 4 main problems. As I said earlier, missing verb readings are really problematic for our parser. As you can imagine, as I've shown to you, the whole MultiNet construction is built around semantic information from deep lexical entries, and if we have a verb reading or a total verb is missing in the lexicon, we have a real problem. We have some kind of a hypothesis mechanism which try to produce lexical information for unknown words, but for example, we have no mechanism which tries to generate hypothetical readings on the fly. A second problematic area are complex sentences comprising many clauses. This is a little bit related to the next point, analysis depth. This means we limit the parsing time, because as you can see, we're parsing quite large resources, so we have to employ some pragmatic limits. And this also costs us some percentage. And finally, if you go from one corpus to the other corpus, it's a real problem to see all the different encodings of special characters. I have mentioned just quotation marks, so we currently have no technology to automatically adjust to the conventions of the corpus. But in this case, for example, if you have a Clay corpus which contains lots of news articles and newswire text, you lose many sentences which are really clear to the parser, but contain some strange conventions for marking up direct speech, indirect speech, things like this. So accuracy, currently we have investigated this only on small samples, but our impression is that we are not that we are in the area of the coverage percentages, because we have the need. As I showed you, the parser always tries to build a complete semantic representation of a sentence, and this restriction acts as a good filter and this ambiguator. So there are some cases, well-known cases like prepositional phrase ambiguity, where we make errors, of course, although we have a specific prepositional phrase disambiguator. But in general, it's not too far away from the coverage. And finally, about the speed of the parser. This is controlled a little bit by a parser parameter, which I've called maximum number of WCF calls. So it's basically a limit how many verb class functions you can call during the analysis of one sentence. And this, of course, limits the coverage, and the current settings that we are using are so that we end up with speeds like 1 to 2 seconds per sentence on current hardware. So, but this is really an important point, the speed of the parser, because if you look at the size of the Corpora we are working with, you end up with something like several months of parser time if you use just one computer. Of course, we use it in parallel on several machines. So now, as I said, disambiguation is one of our research areas, and the Vocadi parsers uses some specialized methods in the following 3 areas: for prepositional phrase attachment and interpretation, for coreference resolution, and for word sense disambiguation in a very restricted form, only in the context of prepositional phrases currently. So I just want to describe the general approach, which is a hybrid method. And you might remember this from the architecture slide. We have 2 components in each disambiguator. First, we have linguistic rules, which we maintain manually. And in addition, we have disambiguation statistics, which we derived from annotated corpora. And on this, for this, we use a statistical model of multidimensional big-off, which I want to explain in more detail. I have an example 2 slides ahead, so I might switch to it on the fly. So the idea is we have a set bold R of all theoretically possible ambiguity problems of one type. Let's say we are talking about coreference resolution, so we're talking about which antecedent candidate is the correct one for a given anaphor. And one element of this bold R is then an ambiguity problem instance and can be represented in general as a list of alternatives. So in this notation, we have a training corpus, which is just a list of elements of the following form. We have a representation of the problem instance, and we have the information which of the alternatives is the correct one. So we have an index in a supervised fashion. And we start with some very simple absolute frequencies, which just count how often does this and this constellation, for example, the first alternative is the correct one. The problem with such an approach is, as you all know, is sparse data. You can do this, but you probably won't be very successful, because what you are counting are very specific constellations. So you need some kind of abstraction. And for this, we have an abstraction function A, which maps for different abstraction levels all kinds of ambiguity problems to some abstraction. So one way to do this, what we do it, is to define this abstraction function from simpler functions which abstract in just one dimension. And I will explain to you what what can be seen as dimension in our approach. And then, so we have, for example, if you have two abstraction dimensions, we can abstract in each dimension separately and then combine with a special combiner and receive the complete abstraction. And if we do this, then we have our levels are from some Cartesian product. So if we have just two dimensions, we have two level sets which are combined by Cartesian product. So this was probably not the best slide, so I will try with an example. Again, let's stay with coreference resolution. The first level we start with is this level 1,1. And the ambiguity problem, which might come from some short paragraph of text where we want to resolve a person pronoun. The initial abstraction looks like this, that we might have, let's say, 3 different antecedent candidates, noun phrases, for example, which can co-refer with the current personal pronoun. And each antecedent candidate is listed here in a separate line. And as you can, I just want to give you an impression how it looks like. Of course, the details are a little more complicated. But basically what we could store on the initial abstraction would be the name of the rule that allows this coreference to occur. This is all in the first column of this table. Then you might want to store the entities, the semantic feature combination of the antecedent candidate. And you might also want to use some other standard features in the coreference resolution. Just for example, I've put here the syntactic case. And so this is the initial abstraction. And the idea of having different dimensions in a back-off model is explained in the following. So in the first 2 steps to these 2 levels, we just do something which I would like to call detail back-off. So we just drop some detail from each alternative. So the important point is we still look at all 3 alternatives, but we look at them a little more coarse-grained. So here in the first step, we drop, for example, the case feature. In the second step, we make the semantic type hierarchy a little coarser, because I must explain this. Substance is in our hierarchy a subtype of con object, so the values are coarser here. So in general, we end up with a representation with less detail. And then the 3 first levels are all concerned with detail back-off, and the rest are concerned with alternative back-off. By this I mean that you drop complete alternatives. As you can see, all these, on the 3 last levels, we only see 2 antecedent candidates, and we have, by some specific convention, we have dropped for example, the most distant alternative. Most distant would be reasonable in the context of coreference resolution. Okay. So just very briefly, this is what happens in the learning phase, where we have to produce, for each level, we have to produce some statistical model by multidimensional backoff. For this, we must first define in which order do we step through the levels. As you can see from on the slide before, this would be a possible order, but of course you can determine the possible or an optimal possible order, for example, by looking at the entropy of the corresponding models. And then what we do statistically is very simple after this. We just count now for every level L all the ambiguity problem instances which map to the current abstraction. So, and then in the application phase, what we do is we calculate some very simple statistics. We look at, first select the first level. We calculate the relative frequencies that a specific alternative is a correct one, divided by the sum that all the others are correct. And we take this relative frequency as an estimate for probability, nothing special here. So, and we have some stopping criterion, for example, if an absolute threshold can be used. If we have some count that is reaching a specific threshold, we can stop. If not, for example, popular problem is in the beginning you just have zeros on the very specific representation. So then you must go on. The idea is you could step down through all the levels I've shown in the example. You do the same calculation as before of relative frequencies and probabilities. So this is the general schema which I exemplified for coreference resolution. As you can see, it's supervised, so we need annotated corpora. We have something like this for coreference, and we also use this for prepositional phrases, where we also have a corpus of 1,000 annotated prepositional phrases. And this is one important part of the parser. It's done during the parse. Now, a more high-level view on coreference resolution. If we analyze a whole text, we parse it text sentence by text sentence, and normally we just resolve the absolutely necessary coreferences. So, for example, if you have a relative pronoun, it really helps the parser to decide early which is a correct antecedent. But all the other coreferences are resolved after all the sentences are parsed. This is just one possibility. Of course, you can also build them incrementally or refine decisions stepwise. But we do it in a very simple regime, parse every sentence, and at the end we do a coreference resolution, which also involves the calculation of probabilities I've shown you, but also does some global optimization of the coreference relation that we calculate. So this is basically similar to the former task in MAC. What we do is that we determine the antecedent for each mention or markable. And coming back to MultiNet, this means that we end up with a lot of so-called equal relations, which now go from the anaphor to the antecedent, to the chosen antecedent, which is hopefully the correct one. And these equal relations can be inside a sentence network, or it can link of course, can link several sentence multinets. So I mentioned the corpus. It's Gecko, which might be not so interesting because it's currently only German. Okay, for the final part of the semantic processing, I will talk a little bit about what we call semantic assimilation. It's basically concerned with the steps that are needed when you step from single multinets corresponding to single sentences to a combined representation for larger elements, for example, a whole text. And we do this post-interpretation step after parsing, mainly to have a clean separation and to not overload the parser. And the main rationale is something like this. We delay all the semantic and pragmatic aspects that need a dialogue model or a discourse model or some kind of domain knowledge. This is all delayed for after parsing. We have implemented some of these things, but so most of them are still future works. So coming back to coreference, for example, one part of semantic assimilation would be to exploit these equal relations which relate to markables of a coreference chain. Of course, this is not, from a MultiNet point of view, this is not ideal, because in MultiNet, a real world entity should always have just one node and not two or three. So in this semantic assimilation step, we just want to merge all the information into one node. Another aspect which we can already handle is deixis. We have implemented the temporal part of it using 40 MultiNet rules approximately. And we have successfully employed this for question answering at Clay of last year. Here's one of the planned items. Currently we do coreference resolution only on single text, but of course an interesting extension which other groups are making is the extension to text collections. So one technique is, or one aspect is, for example, event tracking, when you want to detect all the articles that are talking about the same event, for example. So, as I said in the introduction, the MultiNet representation is one area of research, but we are mainly interested also in applications, and I've listed some of them, mainly the ones that really require or at least benefit from deep semantic representations. Question answering, this is our system called Insicht. We have been participating at Clay since 2004. Clay is an acronym for Cross-Language Evaluation Forum, where we also participate in information retrieval tasks. This is a track called GERD. This stands for German Indexing and Retrieval Test Database. But actually it's covering, right now it's covering 3 languages, English and Russian in addition. And what we apply here is from our semantic toolbox as parsing of documents and queries. And related track at Clay is GeoClay, which is the geographic facet of information retrieval, which really gave us some interesting research area. Of course, the techniques are the same. We use parsing of documents and queries. But interesting part was we did an investigation last year about metonymy, metonymy recognition for location names. And maybe I should give an example. So what we want to distinguish is a use of, say, Prague in a touristical setting or geographical, historical setting from the use, metonymical use in the news that you all know where Prague stands for the Czech government, for example. And we have developed a module which a classifier which tries to distinguish literal uses of location names from metonymical uses following different patterns. This can be found, for example, by work from Katja Markert and Nissim. And the interesting thing was this really worked in this geographic information retrieval setting. We had a huge increase in recall and precision. Normally, in information retrieval, it's really low-level approaches and very, from a computational linguistic point of view. But in this case, it really turned out to work. So, a positive surprise in this area. So natural language interfaces, but I should add the assumption why this is important is that typically the questions, the queries in this geographical information retrieval is about locations in their literal sense. So all the metonymic uses are not interesting. For example, you have a tourist and wants to know all about the beautiful churches in Prague, and they probably don't want to know what the Czech government has done lately. So when you're just looking for the keyword Prague, you will also find, without metonymy recognition, we'll find all the metonymical uses. So we have some natural language interfaces for bibliographic databases following some ISO standard and SQL databases. And lately we had we still have a small project with the EU about which is called benchmarking tools and methods for the web, Ben2Web. This project started really distant from our normal work, but it turned out to be really useful application of our techniques. It's about measuring readability of natural language tests and what is more important, to criticize and to spot problematic regions in German texts. For this, of course, we can use all the techniques I have described before. Many of them, for example, we can concentrate on semantic properties, not so much as other tools on surface-related properties. So we look for ambiguous pronoun references, we look at distant antecedents, and look at all sorts of semantic complexity. So in this project, also the vocabulary parser is a central part in the surrounding modules. Okay. I wanted to show you some details from question answering, just to illustrate that there are really relevant, deep processing is really relevant to these applications, especially because currently most systems are working on a very shallow level. and avoid parsing. Of course, there are important and famous systems like the system from Language Computer Company, for example, and some more. But in Europe, there are not so many systems that work with a semantic parser for question answering. So this is an example question from last year, Clay. The translation would be, in which year did Charles de Gaulle pass away? And the interesting thing about this question was that you only find sentences which are a little bit too far away for surface-oriented systems. So this is a good example for our approach and similar approaches, because you only find sentences like this. Just read the English translation to you. France's Chief of State Jacques Chirac acknowledged the merits of General and Statesman Charles de Gaulle, who died 25 years ago. As you can see in the colors, okay, let's see what InSicht does. Okay, it's an example, you must trust me. It really answered in 1970. So the interesting parts are in color. For example, we have the fact that the blue parts, as you can see, the question used a verb which is only related to the verb in the document, some kind of synonymy maybe. So this only worked because we have these lexical relations in our lexicon. And I should say just briefly that the whole system works by comparing the semantic networks of the documents to the ones from the question and inference steps. So by inferencing, we produce a lot of different alternative networks so that we really can also find related expressions. In this case, the important part was related to temporal deixis, and here the case is that we only have for 25 Jahren, 25 years ago in the document sentence, and what the temporal deixis resolution also needs is the date of publication, and we were able to get this information from 2 points. The one was the official one. There was metadata in all the documents from Clay, so we can just put this in, or in our approach we wanted to work as much as possible with the textual part and not with the metadata, because metadata is a very artificial setting, and in a real world setting you often don't get the metadata. So we get this, the publication date from the start of the article. As you might know, most newspapers start with a publication date, each article. Okay, I'd like to conclude. So our work at the Fernuniversität in Hagen is centered around a deep semantic approach to natural language and understanding. Well, as you have seen in several areas of my talk, and probably in the talk of Professor Helbig, we use MultiNet as an integrating language across all linguistic fields and linguistic levels. So this really turned out to be a positive aspect, especially because we are quite small group of 5 people, so it would be very more time-consuming to work with many different languages for semantic representation. And we have implemented many parts of the paradigm for use on large corpora, and this forms the basic basis for many applications. The example I've shown you was question answer system, which participates at QA at Clay. So some plans for the future. Here's some ongoing work, the extension of the analysis components to English. We're currently working on the English lexicon. This is constructed in parallel to our German lexicon, Hagenlex. And in addition, we try to parameterize the WCFs, the central part of the parser, for English, which is not too hard because the languages are not so far away from each other, as you know. And for German, as you remember, the one slide was the 60%. We have some work to do there. And finally, semantic assimilation has some missing blocks which we like to fill, intertextual coreferences, like event tracking and entity tracking, that you want to determine which person named Müller in which instance occurs in which text of a large corpus. So now it's time for questions.
Maybe all of my questions are just due to some that I have overheard or overlooked some of your explanations. So one question is, if I understood well, you assume or your system allows for having several valency functions or semantic rows attached to one node. I mean, one node may depend, if I can use dependency terminology, on another node in several different relations?
Yes.
So it's not the kind of Fillmorian approach where you just can have one role for one.
This is a small departure from Fillmore. I can go back, but maybe when we started to build the lexicon, we really had the hypothesis that each argument can be linked with exactly one relation. But we discovered some cases where there was the alternative to create an additional relation, or we could imagine to use some pair of relations. So actually there was some discussion because as I have presented it, and as you as you correctly understood it, there is a possibility to use many relations for one argument, but in practice we have something like maybe 5 pairs which occur. So we could easily we could easily label them and then
just one
go back to Fillmore.
Yeah, thank you. Another point concerns the you mentioned presupposition, and that was in the context of lexical. I mean, I would translate it into lexical presuppositions. I mean, presuppositions which are connected with some lexical items. Have you thought of entailments like presuppositions to be drawn from the from sentences, not just lexical items?
No, I have no.
Because that's one point which I think is should be considered when trying to make a network and disregarding the input sentence, the structure of the input sentences, because some of the presuppositions of the sentences depend on the entailments depend on the structure of the sentence, of
You
the
mean
particular sentence.
the word order,
Yeah,
intonation.
things like that. Then you said that some of the problems concern complex sentences where you have several clauses within one sentence. I think I would reformulate this, that these problems arise from coordinated structures. I mean, you don't need to have many clauses, coordinated clauses, but also with coordination of simple words, so to say. I think that's something which we observed when we annotated our tree bank, that many causes of the disagreement of annotators concerned the coordination, the analysis of coordination, coordinated structures, maybe even simple words. So that's one point. Then, when you spoke about co-reference, I think it's useful to distinguish textual co-reference and grammatical co-reference, because with these grammatical co-reference, you can rely on the grammar of the sentence. Like you have control verbs, he decided to come, and then the subject of the infinitive co-refers with this particular verb with the actor of the main clause. But with some other verbs belonging to another class, this kind of co-reference is different. But it is given by the grammar, by the properties of the verbs, of the classification of the verbs.
Yes.
That's, I think, different from the textual co-reference, where you co-refer to some within the text, but not. But it's not reflected in the grammatical rules. So, it's something we distinguish in the prior dependency tree bank. And I think it's pretty useful for the work of co-reference.
We think we use this distinction too, because if I understand it correctly, grammatical co-reference is never ambiguous, because if you have a correct...
well, it may be ambiguous, but then the ambiguity is
somewhere else.
Seen from then the grammatical structure is ambiguous, which can be, but otherwise it's more. You can determine the co-reference more easily.
So in our co-reference resolution, such cases wouldn't be handled because it's considered to be stable, to be unambiguous.
And my last question concerns again co-reference. If I understood well, and maybe I misunderstood you, the relation of co-reference. The type of relation you treat is the identical, equal, but there are other kinds of co-reference, and I would be interested in your co-reference corpus. Do you mark the different kinds of co-reference relations?
Currently, we only annotate identity. Co-reference. But as you can see, by looking at the rule names, they all start with this prefix ident. So this is a small indicator that we really wanted to extend it. We have some rules for other types of co-reference, like part whole, things like this, and we really would like to try out the approach to determine globally optimized co-reference resolution with looking at different co-reference types at the same time. So the problem is not to write the rules that license these possibilities. Problem is that we don't have the corpus right now. But we also would like to look at the two buts, because as I know, they already annotated a lot of co-references, almost 90% of the whole corpus, and also trying to identify other types, but
Yeah, so
not all types.
We should look at that because we are now engaged in marking or annotating co-reference relations, and we distinguish 4 or 5 types, and I think it's too few. So that's why I ask you whether you have some other types. Okay, thank you. So now,
recently, I have been reading some articles about MultiNet, what is Microsoft Research project, and it seems to me, at the first glance, superficial, that there is some resemblance or connection between the MultiNet of Microsoft and MultiNet of your group. Is this true? Can you tell me something about it? Are you inspired by them?
No, we're not inspired by this, because the formalism, I guess, of MultiNet is almost started 20 years ago, so it can't be inspired. We know about this. Isn't this by Microsoft China, maybe?
No, it is in, I suppose, in Redmond. There are names,
okay,
I remember, Lucy van der Bende and Bob Dolan.
Yeah, okay. We have a paper, not me, but Professor Herbeck paper comparing MultiNet to some other semantic network formalisms, and there is a small passage about MultiNet, I guess. So I'm sorry, I'm not a MultiNet expert in research. I'm just using it as a representation.
I have just one question about the coverage question you mentioned, because and the question is, you have your corpus, the Hagen Lex data, where you can actually compare not just the coverage but also the accuracy on at least some respects.
Yeah,
right?
We have done this.
But and then you said you only did the accuracy on small samples. So what is your guess, let's say, how much from those 60% you can cover is actually also correct?
My guess would be something like 80%. If you are, maybe we have excluded the problem of word sense in this sample. So if you can live with word sense errors, it might be around 80%.
My question is, you were speaking about the German branch of WordNet, GermNet. Can you tell us some details about the, how to call it, cooperation with the GermNet and MultiNet?
Yes. We started as normal users of GermNet. So we bought the license, as all the others must do. And then the interesting part is that we have, together we have 2 interesting resources. Our Lexicon is semantically based and quite large in coverage. And of course, GermNet has something like a factor of 3 or 4 more entries, but no information about which is needed for parsing, for example. So we started to cooperate in several ways. For example, a prerequisite which we needed was a mapping of our concept IDs. You remember this given .1.2, we had to map them to GammaNet because they use a completely different concept world. And this turned out to be quite difficult. We have some cases which we were able to do automatically, but many cases must be decided by annotators. And in general, the impression is similar to WordNet. GammaNet has very fine distinctions, and we have coarser distinctions, just in general. This is especially true for nominal concepts, and this is a little bit related to our strategy in the lexicon. We only distinguish readings if they can be distinguished on the MultiNet level. So in some cases, for some nouns, readings collapse. And then we have the information that 2 or 3 GammaNet readings correspond to our reading. And then we did some interesting consistency experiments. So we have some form of hierarchy, semantic hierarchy. GammaNet is a big hierarchy. So we are able to calculate some misclassifications. On the one hand, we profited a lot because we could correct things. On the other hand, we were able to send some hopefully helpful commands to Tübingen. So we are always trying to provide some input to the GammaNet project. And the whole thing got a little bit more organized by my colleague Rainer Oswald. He has been already organizing two workshops together with Tübingen about lexical ontological resources in German, but also in other languages. So it's continuing.